So I will be taking a step back, because yesterday I talked about 2 black holes. Now I will discuss only 1 black hole, or how a supermassive black hole, which we know exists in centers of galaxies, might have formed. And so this is really a puzzle that is now 10, 15 years old in astronomy. And I hope you'll find it intriguing and you learn something. So if you don't work on this topic. I should say we'll discuss this topic further in the workshop, so if you're enticed by the talk, you should come tomorrow. There will be a talk, and later in the week I'm sure there will be discussions. So my talk is roughly is outlined as follows. So I want to spend the first 2 parts on background, discussing the observational situation of high redshift quasars and why we think they're very massive black holes in the early universe. And then the basic theoretical framework of the formation of the first stars and how they leave black hole remnants behind, and which we can then use to grow them into bigger black holes. This is, by the way, is the number of slides I have prepared, so you can see what I think will be the most important topic. So the second half will be the main part of this talk, theoretically explaining or modeling the formation of these big black holes. First using the stellar mass black hole remnants of the first stars and trying to grow them. And then the second part, which as you can tell, I think is twice as more likely to be correct from the number of slides, is the very rapid collapse of gas in special environments in the early universe into massive black holes. And then, I don't know if we'll have time for this, but there is the question of how you actually discover the truth from observational data, and I do have some potential ways of doing that in the future. Okay, so the first part is observational situation. Again, if you haven't followed this topic, it's pretty easy to summarize. So around redshift, around 10, 15 years ago, we've started discovering very bright quasars at redshift 6 and above, which is when the age of the universe is about 1 giga-year or less. And there are about 30 of these. They were only discovered in the Sloan Sky Survey, which is very bright, very shallow but very big survey, so it discovers very rare bright objects. And then subsequently a couple of dozen in other surveys of the sky. So the record holder, just so you know, currently is a redshift 7.08 quasar. The age of the universe then is 0.77 giga-years compared to the 13.7 giga-years now in this infrared survey. Now we have 3 dozen of these objects. They're very bright, and they're probably the tip of the iceberg because we only see the brightest quasars from these very distant epochs. And the space density of these objects is about 1 per cubic gigaparsec, extremely rare. Sort of 5 sigma tail of the luminosity function of quasars, or the underlying halo mass function of dark matter halos. So there's probably a huge number of more quasars at high redshift which are slightly dimmer. Now the most important point is that these are probably powered by very massive quasars, and you can do this estimate in a few ways, but the simplest one is to say, I know the luminosity of the source. I know there's a limiting luminosity for a black hole, which is the Eddington luminosity. You cannot have a much higher luminosity. And so if you assume that they're radiating at the maximum Eddington luminosity, then the black hole mass simply comes out to be a few billion solar masses, because these objects are so bright. You can actually also estimate the halo, the dark matter halo, the host which hosts these quasars, the masses based on the matching the abundance of the observed objects. So with this 1 per cubic gigaparsec observed, the halo masses which have this space density is about a Milky Way size halo. So do you think they sit in, and these are sort of 5 sigma objects, these are very rare. Milky Way size halos in the early universe are very rare. So we think these big black holes sit in big halos at high redshift. Now, the reason this has become a very active subject of research is basically that there is a slight problem in growing such big black holes in at least the most naive picture, where you assume that you start with a stellar mass black hole. I'll explain how that works later. But you start with a stellar mass black hole and you grow it at the rate which corresponds to the mass accretion rate m dot, which would give you at every mass the Eddington luminosity, the maximum luminosity. So then you find that the growth of the black hole would be exponential, because the Eddington luminosity is linear with the mass. So if m dot is proportional to the mass, it will grow exponentially. The e-folding timescale is about 40 million years. So in this simple plot, I collated the data where I show the redshift and the mass, the black hole mass of the discovered quasars. And then this red curve is coming from high redshift, assumes that we had a 10 solar mass black hole at redshift of 35. Again, I'll explain this a little more detail later. And then we have a background universe, a standard model from cosmology. And then this black hole is allowed to grow exponentially at this Eddington rate. Then its mass will be this red line. So there's actually two of these, which are two of the quasars, including the record holder at redshift 7.8, which is above this line. So you can't, if you believe they can only grow at this Eddington rate, you cannot grow to such a large mass. And even the rest of them, they're very close, which means you basically have to continuously grow at near the Eddington rate at all the time from the beginning of the universe to explain these large masses. So I will discuss whether that's possible. There are other obvious alternatives, which is merge many black holes together to try to grow them, or grow much faster than this Eddington rate during a burst of accretion. Before I leave the observations, I should say it's very good to ask yourself, are we being fooled? Is it possible that these black holes are actually not billion solar mass black holes, but much lower mass, let's say 10 to the 6 solar mass black holes? And you could make them much brighter, so they appear much brighter. At least there are two ways of doing that, and the short answer is they don't work. But one is gravitational lensing, and just very quickly, that doesn't work. So you could say these are 10 to the 6 solar mass black holes, extremely magnified by gravitational lensing. They're very rare objects. The reason that doesn't work is that you would actually predict a second image, which would be detectable with the Hubble Space Telescope, if you want to magnify it by that much. And we looked with Hubble, and there's no second quasar. Beaming would be another option, where you take all the luminosity and beam in our direction. That also doesn't work, because these quasars have very normal spectra. And quasars produce broad emission lines, which are produced by the ionizing radiation from the quasar over its entire solid angle. So if all the radiation were beamed towards us, and that's what we will be seeing, the rest of the 4 pi angle would not be producing the broad lines. So these should then have very weak broad lines, which is not true. These quasars have normal broad lines. And then thirdly, there's actually a mass measurement from reverberation mapping. So in very low redshift quasars, we can measure black hole masses by a technique which I won't explain now. It involves time series data called reverberation mapping, and you can measure black hole masses at low redshift quasars, and you can empirically find that it's related to the widths of particular broad lines in the spectrum. So in these high redshift quasars, based on this method, if you believe the calibration is valid at high redshift, you find that these Eddington ratios, that basically the masses are a few times 10 to the 9 solar masses. So these quasars are indeed shining at the Eddington limit. This here is the luminosity and black hole mass. This line here is the Eddington luminosity. These are the quasars that exist at redshift 6, and they're shining at the Eddington luminosity.
For the non-experts in the audience, explain what this Eddington rate is.
Okay, so the Eddington rate, this is very simple. You equate radiation pressure from so you have a black hole, it's radiating. Actually, it doesn't even have to be a black hole. It can be a star. And you radiate, and the gas that's falling in is feeling radiation pressure. The electrons, because of electron scattering, are hit by the photons coming out, and the momentum of the photons pushes the electrons outward. And you equate this with gravity pulling the electron and the protons inward. And if the radiation pressure is higher than the gravity, then in principle you can't swallow the gas. It's being blown away. So if you take a black hole and you make its luminosity higher than this, it can no longer accrete. That's the Eddington limit. Okay, so let me say some good news. So, well, first of all, how do we explain these 10 to the 9 solar mass black holes? And as I've already mentioned, there's basically two kind of explanations. One is to take the first stars in the universe, assume they leave behind stellar mass black holes and grow them, or you can try to make models or postulate and explain that the growth can be much faster than this fiducial Eddington rate. Now the stellar mass black holes, it's a good idea, but it does require this uninterrupted accretion throughout the age of the universe. And there are some dangers in this scenario. In particular, you have to be surrounding your stellar mass black hole all the time with dense gas so that it can continuously accrete. And these black holes probably sit in very small, tiny galaxies, 10 to the 6 solar mass mini galaxies in early times when the potential area is very small. The black holes are easily displaced from the dense centers and ejected even. And the particular problem I actually want to address here, because it's interesting, is if you actually assume that all the early galaxies have stellar mass remnants which can grow at the Eddington rate all the time, you can, as I'll show, explain the 10 to the 9 solar mass black holes at redshift 6, but you'll end up producing a huge number of slightly lower mass black holes which are overproduced. Now the direct collapse, so-called direct collapse camp of people working on this, or you can call this heavy seeds, it basically says that I can make a 10 to the 5, 10 to the 6 solar mass black hole at some high redshift, essentially ignoring the Eddington limitation, just the gas falls in very rapidly, and either collapses directly to a 10 to the 5 solar mass black hole, or makes a 10 to the 5 solar mass supermassive star, which then leaves behind a 10 to the 5 solar mass black hole because it's unstable at the end of its life. Or maybe it actually forms a star cluster, and these stars are so unusually ultra dense that they can collapse into a black hole. So the requirement in this picture is you have to have gas falling into center of some galaxy extremely rapidly, and you must get rid of angular momentum of the gas very rapidly, and you must avoid fragmenting too early and just make a bunch of stars. You want to get the gas into the center. And this is actually, so this is my expertise of research, is that this requires that the gas cannot cool down to low temperatures. So this may be slightly, if you don't work on this, it's sort of amusing, but the fate of the gas or the first stars and the first black holes is basically dependent on molecular hydrogen chemistry, because the primordial gas falling into the first galaxies can make molecular hydrogen. Molecular hydrogen radiates, cools the gas down, and if you make it too cold, it's prone to fragmenting gravitationally. It becomes gravitationally unstable. So the trick to this picture is to get rid of the molecules which would cool and fragment the gas. Now, the good news is that we do think there are lots of primordial stars leaving behind stellar mass black holes. In fact, I like to start with this slide, which has nothing to do with the rest of the talk. This is the power spectrum of fluctuations from cosmology, as measured by microwave background experiments and large-scale structure experiments. And I want to emphasize that the formation of the very first star in the universe is essentially almost known. It's a no free parameter cosmology problem, because we know this is at inflation, this is the density power spectrum, density fluctuation power spectrum, and these are scales here. So this is 0.1 inverse mega, so this is roughly 1 megaparsec, this is 0.1 megaparsec, or in terms of mass scale, this is 10 to the 15, 10 to the, let's say, 12 solar masses. And the only thing that we need, so now we need to evolve this density fluctuations forward in time, and you form dark matter halos hierarchically. First you form small halos, then they merge and make bigger dark matter halos. And so this process is only gravitational instability and structure formation, and it can be modeled and simulated without free parameters. And the only thing is that we are actually looking at the very first dark matter halos. So those have masses of 10 to the 6 solar masses or 10 to the 5 solar masses. So they're forming from the perturbations, which are extremely small scales down here, maybe 100 times smaller than I actually measured by these experiments. So we're extrapolating the power spectrum from what inflation is predicted to be a power law down here. Once you believe that, you can take an n-body simulation and you can find how many halos, dark matter halos form at what redshift. This can be done at redshift 30. The simulations of structure formation going down well below these small masses. I like to point out for cosmologists, the only uncertainty I think here is warm dark matter. If you change dark matter and you mock with the power spectrum, then things can be different. But if you believe in cold dark matter, we know how many million solar mass dark halos there exist, and we can simulate the gas collapse into such halos. So this started actually 10, 15 years ago as well, theoretically. The first simulations were just after 2000, and this is a recent one where this shows density distribution in a dark matter halo which has a mass of 300,000 solar masses collapsing at redshift 20. So this is now not an n-body simulation, this is a high-resolution simulation of an individual halo with the gas in it. And these panels just show the time evolution. And the key thing that happens here, so this is actually ridiculously high resolution, because this starts from cosmology. You follow the halo as it forms, and the gas falls in it and forms molecular hydrogen. The gas cools. And the length of this box is 10 AU. So we're basically seeing solar system scale. We're almost seeing a star forming here, starting from cosmology. And what happens to the gas is it becomes few hundred Kelvin because of the molecular hydrogen, and forms these clumps, these clumps have of order 1 solar mass. And there's very high density. We haven't actually turned on a star, and these clumps are still accreting, so we don't actually know. We're in the borderline case. We're almost formed a star, but not quite. These are the protostars resolved, and they're accreting. And now you can ask, okay, but what kind of star forms there, and what remnant it leaves behind? So there is actually a simple argument for estimating the mass of the star that forms there. And it goes as follows. So the temperature of this gas is known. It's about 100 Kelvin. So the sound speed from that temperature is just about kilometers per second. And the self-gravitating gas clump then has an accretion rate which goes like sine speed cubed over g. This rate is about few times 10 to the minus 3 solar mass per year. And this is back of envelope physics, but you see it in the simulations. The rate at which these clumps accrete is roughly this. And the star mass that forms there is therefore this accretion rate times the so-called Kelvin-Helmholtz time. That's how long it basically takes for the protostar to evolve and turn into a star. That's about 10 to the 5 years. So you would form a 100 solar mass star, is the prediction. Now, this is really an upper limit, because you could actually you could get smaller stellar masses if you don't actually grow up to this 100 solar mass, because the gas, as it tries to accrete on a clump, it fragments, or because it starts radiating and the radiation itself limits the star to a lower mass. But maybe I won't go into details here. The point is that you still get a very massive star, as far as we understand from these processes. In fact, this particular paper treats the radiation feedback on this protostar, and the answer is 43 solar masses precisely. So that's interesting. Here is then the last bit of the story, is where you can ask, if I have a star which is different from usual stars because it has no metals, it's made purely of hydrogen and helium, and it has a mass of 40 solar masses, what happens to its stellar evolution, and what happens when it dies? So this paper summarized the fates of stars, and this axis is metallicity of the star, so we're only interested in z equals 0 down here. This is the mass of the initial mass of the star. And what you can see here is, if the mass is bigger than 25 solar masses, then the star basically leaves a black hole remnant. Initially, it actually has it starts to blow itself apart, but doesn't make an explosion or a supernova. The gas falls back, and the entire 25 solar mass is left behind as a black hole remnant. In fact, this goes all the way up to 140 solar masses, where you get a black hole at the end. I won't go into details. There's a narrow mass range where you might get a pair instability supernova. Let's ignore this. And just the conclusion from here is we can simulate from cosmology the number, the early halos. When the halos build up to a mass of 10 to the 6 solar masses, dark matter halos, They form stars, we think they're massive, and we think they leave behind these stellar mass black holes.
Just to make sure, so the statement was that under the assumption that there is all dark matter, then this is robust.
Yes, cold dark matter gravitationally fragments into dark matter halos. There's really no way to avoid this. And you can simulate what happens to the baryons. And we can put in the cooling and the molecule formation. There actually is no free parameters.
In this simulation, do you see the supermassive black holes as
No,
well?
actually I'll do, so these simulations get up to this point where there's this small, tiny actually I like to call them micro galaxy because it's exactly 10⁻⁶ of the Milky Way. So it's a micro galaxy. And it forms these dense clumps, and then we have to stop the simulation because it becomes too dense. So we don't actually run this kind of simulation all the way up after the stars form, the hierarchy of halos, all the way to larger halos where there might be supermassive black holes. We just stop here. And the reason is not it becomes impossible to run it further. The time steps of a simulation becomes too short due to high density.
Maybe you can reduce the resolution and go to higher masses.
But then, actually, I will show a simulation later where we go to a higher mass scale. So maybe you can ask them later.
I have a question related to that. Do I understand correctly that the change of paradigm in 2018 now, when people believe in 100 solar masses, and now people believe in multiple fragments of
Yeah.
does not change the conclusion, because if you go to your plot,
Yes.
eventually you always form a black hole.
So you're correct, actually. This paper was a big milestone in the field. All the papers before this essentially saw no fragmentation. So it didn't look like these little clumps. They didn't resolve them. This was a high resolution, and they found them for the first time. So, but it doesn't change the story, because all we require is for one, and because it's not like it's fragmenting into millions of pieces, it only fragments into a few pieces. And we only want one of these to give us a stellar mass black hole. So I don't see any, maybe half the time that doesn't happen.
Just a quick comment.
Yeah.
That's the first paper, but Tom's student saw the fragmentation before.
Yes. Yeah, we can. There are a few others which so fragment, but some of them are different. They fragment on larger scales. Anyway, I don't think this conclusion is going away. That you get, looks like you're getting massive stars in these first halos. Okay. So let's try to first grow these stellar mass black holes to supermassive black holes. Now this exercise is also in principle very simple. You can do it at home because we know how dark matter halos are assembled, again unambiguously. So this so-called merger tree here represents, the white part represents the buildup of a galaxy, the dark matter halo of the galaxy. So this extends down to each branch when in the hierarchical structure formation this halo mass is, let's say, 10 to the 5 solar masses. The escape velocity then is actually a few kilometers per second from these halos. And you might start, so these branches, of course, you could continue all the way to redshift 100 if you want, but then the halos are too small. They won't actually form gaseous objects because the pressure of the gas prevents the gas from flowing into the dark matter halo. So there is actually a limit of the star formation, which starts when the halos rise to about 10 to the 5 solar masses. So you simply take a redshift 6 dark matter halo of the size of the Milky Way. You know how to make a statistical realization of its merger tree. And you can say I put in each of the branches, whenever they cross 10 to the 5 solar masses, I put a stellar mass black hole. And then that's in black here. And then I simply say, in the optimistic case, each black hole has some initial mass between whatever 10 and 100 solar masses, and then it's starting to grow at the Eddington limit, regulated by the Eddington rate. And then whenever two halos merge, the most optimistic thing you can do is merge the black holes together. So that's a simple picture. Again, we made some major assumptions, which is that the black holes can continuously grow throughout cosmic time at the Eddington rate, We also assume that they merge, the black holes actually merge when the two microgalaxies collide. The black holes are brought to the center and coalesce. So I don't think I have, and these are major assumptions. Maybe I should skip these details. Well, just to summarize, so this exercise can be done, this cannot be done with a numerical simulation because we want to simulate a volume of order gigaparsec, and we want to resolve down to these 10 to the 5 solar mass halos. So we cannot do that directly. So we have to rely on these Monte Carlo realizations of the dark matter merger histories. And there's really these three, which we did a few years ago. So there are these three major assumptions you have to deal with. One is how often you have a seed black hole. And the answer could be, well, most of the halos have a seed. What is the time averaged mass accretion rate of each seed? And as I already said, we allow it to grow at the Eddington rate. And then I think that's particularly interesting for the workshop participants. What happens with the two black holes when the halos merge? So that's here, for example. And that's very interesting because we assume gas drag leads to coalescence, but as you know, there's gravitational recoil. So that was actually one major reason we did this calculation, is, as I said, the escape velocity from these early, very tiny microgalaxies is a few kilometers per second. When two black holes merge, they recoil due to the anisotropy of the gravitational waves emitted at the coalescence. And those recoil speeds are hundreds of kilometers per second, typically. So it's very easy for a pair of black holes in these early galaxies to just fly out of the dark matter halo. So that has to be folded into this model. If I'm allowed to show a few specific plots here, so this is an outcome of such a merger tree calculation. This is cosmic time, so this is 1 gigayear, this here is 100 million years. This is redshift on the top, and this black one, this black curve shows the mass of the most massive black hole we have at each cosmic time, and you see it goes to a few billion solar masses by redshift 6. So that's good. The volume that we've simulated is actually comparable to this gigaparsec volume of the surveys which found the black holes. So indeed, roughly in the observed volume where there should be a few billion solar mass black hole, this process makes one. So that's the good news. The bad news is, and I should actually just clarify, this is an interesting peculiar scenario where this recoil doesn't hurt. And that's because what happens in these models, the way you get up to these large masses, is that you have a very lucky early branch in this merger tree. Let's say redshift even 45, which is an extremely rare perturbation, but it has formed a microgalaxy at redshift of 45, and there's by assumption, there's a black hole seed there, which is starting to grow. And then by the time that very early one undergoes its first merger, it has already grown by a factor of 100 in mass. So it's already a, say, 1,000 solar mass black hole. And then when it merges with the newly formed black hole, which is 10 or 100 solar masses, it has very unequal mass ratio. And the merger recoil is actually very weak for unequal mass black holes. So it doesn't get ejected. And then it grows even more. So this is like the rich get richer scenario where this lucky early seed avoids merging and getting ejected and grows even more, and then is always massive than its merger partners, so it can continuously grow. So that's how you end up with this big black hole. And the bad news is that the blue curve here, just look at this one. This shows the total mass density in solar mass per cubic megaparsec of all the black holes we've produced in this kind of model. And as you can see, this is about 10 to the few times 10 to the 7 solar mass per cubic megaparsec. Now this is a big problem because we know what is the local mass density in supermassive black holes in galactic nuclei. This we know because we've looked at 100 galaxies. We know the black hole mass in these local 100 galaxies, and we extrapolate and it's correlated with the masses of galaxies, and we extrapolate and we say all the galaxies have black hole masses obeying these correlations. And then you find in the local universe there's about 500,000 solar mass per cubic megaparsec of supermassive black holes. So moreover, we know that most of this black hole mass has actually grown around redshift 2 or 3, because we see luminous quasars which peak and their activities at redshift 2 or 3. And the mass you have to accrete to produce all the light output of quasars is basically comparable to this number. So you have to accrete this much mass just to explain the redshift 2 quasars. So at most 10% of this could be present at redshift 6. So that means we've overproduced this total black hole mass density is about 1,000 times more than we would want. So that's a big problem. And we can solve this problem in a few ways. So we have to we can basically throw away this simplest model you can think of. You have to come up with a reason why you're suppressing the 10 to the 6 solar mass black holes, which dominate this total mass density at redshift 6, without killing the 10 to the 9 solar mass black holes. And there's a few ways to do that, which, but one would be, maybe I won't go into the other two. One obvious thing you could say is, well, the black holes are left behind, which we input into this model every time a galaxy goes above the threshold, and we put stellar mass black holes. Maybe that stops below some redshift, because the gas is now metal polluted by previous star formation and fragments into small normal stars and doesn't produce these massive stars, which give you frequently the stellar mass black holes. That's just very hard to make this actually work in practice. The more general idea, which I think works very well, is feedback, and that's very natural because I haven't yet said anything about the radiation that's coming out from these stars and black holes. But in fact, in this model, we're building up stars and making black hole remnants, which we're allowing to accrete. So of course, radiation comes out. And they produce infrared, UV, and X-rays. Now, these backgrounds can actually make background radiation throughout the entire universe because you have many sources. They're of course rare compared to present-day galaxies, but they're still populating the entire universe with these stars and black hole remnants. And you're producing radiation, you build up a background. These background radiations, it's a very important point. These global backgrounds can regulate the early star formation history in general. Because so far I've assumed every small galaxy is forming in isolation from cosmological perturbations. But in fact, these rapidly building backgrounds will invalidate this, because my micro galaxy will be forming embedded in radiation fields coming from all the previous objects. Now, a particular thing, and I guess I will again cut this short a bit, this can affect the molecular chemistry, but I think let me focus on X-rays. Since I'm saying there are stars which leave behind accreting black holes, you can ask, well, what happens due to the X-rays which come out of these accreting black holes? And you have to assume a spectrum. So the key point here is if you have a 100 solar mass black hole and you take the simplest bet for its spectrum when it's accreting near the Eddington rate, it will look like this. It will have a disk and a corona. It doesn't really matter the details of this spectrum. What matters is that it peaks in the few keV range. Even up to, when you grow the black hole to 10 to the 5 solar masses, this toy model spectra, they will produce 1 to 5 keV radiation. Now the universe at these early times is consisted, the background universe has neutral hydrogen gas, but it's optically thin at few keV. So these photons just go everywhere, and they will heat up the intergalactic medium and make it hard for the gas to collapse into the next generation of small galaxies. And even if the gas does collapse in the next generation of galaxies, it has excess entropy. So the core of the gas inside the halo is less dense than it was without this background. So hopefully this makes sense. So you have now a model where stellar mass black holes are left behind, they're accreting, but producing also X-rays, which are heating up the entire universe and preventing the formation of new stars in next generation halos. Actually, no, you cannot reionize the universe with this, because the X-rays, so this gets into details, but a KV X-ray is injected into the intergalactic medium, ionizes a hydrogen atom, you get a photoelectron, a KV photoelectron, And when the universe is neutral, it's mostly going into heating. The energy is mostly going into heating. But once the universe is 10% ionized, the energy initially can go into ionizations and heating. But once the universe is 10% ionized, it all goes into heating the electrons. So even if you inject huge amount of X-rays, you will be at most 10% ionized. But that's a very good question, because I won't go into this, but there's a constraint on this from the new Planck optical depth, which actually is in favor of this feedback I'm just promoting, that you have to shut off star formation early on. So the bottom line is, we call this scenario global warming. I think this is actually the perfect term, because there's a generation which pollutes the universe and heats it up, and only the next generation suffers the consequences and is inhibited. So this is global warming by X-rays, and this is now the density of black holes in the entire box, including all black holes. It basically comes down to the limit that is consistent with the no number. And if you go back and forth, with and without this feedback, you can see that the big black holes are not hurt at all, because they're forming from these early seeds which run away. They could reach a critical mass or before this global warming set in, but all the smaller black holes later on, they're eliminated. Okay, very good. So now let me go to the last I guess 15-20 minutes to what I think this scenario is appealing. I think the biggest problem with this scenario is that we do have to assume that the black holes continuously grow at the Eddington rate, and that is not guaranteed to be plausible, given that the black holes, for example, one objection to this, the star which left behind the black hole could ionize the gas and eject it from the halo, and then the black hole finds itself in low density medium. Or the black hole just moves around and doesn't sit in the very dense center of the halo and doesn't accrete, just doesn't have enough gas density around it to have a supply near the Eddington rate. So it's very interesting to explore this other option, which is much more rapid formation of bigger black holes. So switching gears now and focusing on this. So the key idea in this picture is the rapid collapse of gas into early galaxies. Now, as I said before, the gas falls into these 10 to the 6 solar mass halos at a rate of 10 to the minus 3 solar mass a year. That's coming from the molecular cooling, which determines the temperature. If you could make this more like a solar mass a year, then you could, instead of accreting 100 solar mass in this Kelvin-Helmholtz time, so remember I said the 100 solar mass of the star is because you have 10 to the 5 10 to the 5 years to make the star due to the Kelvin-Helmholtz time, and the accretion rate was 10 minus 3, that gave you 100 solar masses. If the rate instead was a solar mass per year, then you could end up with objects which have 10 to the 5 solar masses, so supermassive star. For this to happen, you have to get rid of angular momentum. So you either need a large viscosity, or you need a very rare object where the angular momentum of the gas is very small. And you have to avoid fragmentation. So you have to avoid cooling the gas down to very cold temperatures when it becomes prone to fragmentation. In particular, you have to get rid of the molecular hydrogen. If you didn't, then there would be just these so-called POP3 massive metal-free stars. Maybe I'll skip this here. So there's a promising site where this happens, and there's only one key physics that you now have to digest, which is there's these halos whose virial temperature is 10 to the 4 Kelvin. They're sometimes called atomic cooling halos. In practice, these are halos which are about a factor of few hundred bigger than the 10 to the 6 solar mass halos I described earlier. And the distinction is that if the gas just fell in adiabatically into these halos, the potential well is deeper in these halos, so they're 10 to the 8 solar masses, let's say, instead of 10 to the 5 or 6. So the potential well is deeper, the gas heats up more, and would reach the temperature of 10 to the 10,000 degrees Kelvin. This is a magic number, because at this gas temperature, when hydrogen atoms collide, they can excite the Lyman alpha transition, and the gas is now able to radiate extremely efficiently. So if you have gas sitting in a dark matter potential, whose virial temperature, or basically the depth of the potential, is this deep, then the gas will fall in and will radiate extremely efficiently, just emitting Lyman alpha photons. Now, that means it can deflate its pressure. The gas is cooling efficiently, and the gas can flow to the center in quasi free fall and very high rates. So again, this is in distinction from a lower. If a halo is smaller than this and the gas falls in, it cannot use the Lyman alpha. It has to make molecular hydrogen, which cools less efficiently, but it goes to much lower temperatures. So the gas ends up colder and more prone to fragmentation and cannot flow in as easily. So that's the key physics. So this is the promising site. If you have in the universe 10 to the 8 solar mass dark matter halos, which managed to not form stars previously, and manage not to have molecular hydrogen in the primordial gas, then they remain at 10 to the 4 Kelvin, and the gas comes in very rapidly. I don't know if people find this, sometimes people find this paradoxical. This is hot. The key is for the gas to remain hotter so that it can fall in faster. That sometimes people find this counterintuitive because the gas is hotter, so there's more pressure. But in fact, what matters is the sound speed. The sound speed is higher, and the gas just flows in faster. It could be delayed because of the pressure, but eventually it comes in much faster. So it's important to get rid of the molecular hydrogen, and important not to have previous stars, which produce metals, which can give you even worse cooling. Okay, and if you have this situation in this so-called atomic cooling halo, then there's actually a lot of proposals in the literature of how to then create a 10 to the 5 solar mass black hole. One is that make a 10 to the 5 solar mass supermassive star, just by directly ending up with this massive star in the center of the halo, and then we know from general relativistic instability at the end that makes a black hole of comparable mass. You might also fragment into a very dense star cluster, which can still leave this big black hole if the star cluster is so dense that it undergoes core collapse, for example. In any case, let me just show you the key, what I think is the first, gets rid of the first requirement in this process, which is the molecules. So this here is a hydro simulation we did a couple of years ago, and this goes back to your question of what happens, I guess, on a bigger mass scale. So this is a 10 to the 8 solar mass halo. It's collapsing at redshift 14, so it's a later stage in the hierarchy. But we have done something which is the key to the solution. We have illuminated this halo with a UV background, which I explained actually is built up, some UV background is built up in the universe. And the normalization of this background was chosen, so there are no units here. J is the flux seen by the halo. In some units which it doesn't matter, we've chosen a value of 1000. So you should remember this is actually a high number. So if you do exactly the same simulation as, I guess going back to the, in the beginning, I showed you this simulation. So we've done something basically exactly the same, but in a few hundred times bigger halo, except illuminated by this UV radiation, so it doesn't form stars until it gets to this large mass. And then we find the interesting result that this promising condition of large gas inflow is actually realized. So this shows here the density, temperature, Mach number, and velocity divergence field of this dark matter halo at redshift 14. This has a size of about fraction of a kiloparsec across. And the point is that maybe the Mach number, you can see what happens, the gas flows in, it shocks, heats up to the virial temperature, 10 to the 4 Kelvin, and then roughly stays there and just flows into the center of the halo at this high temperature. So to summarize, well, and then here's the bottom line. We can measure the mass of the central object by, so this plot shows spherical shells we place around the center of this simulation, measure how much mass is enclosed. So this is the center of the box. This is going out in the box, which encloses more and more mass. And then we can see the velocity at which the gas is falling in, and we can ask how long does it take for this sphere to collapse to r equals 0 and become part of the central object. So that's the accretion time scale here. And then we've done several simulations where there's no radiation background, or where there's this large radiation background of 1,000. And what you see here is that the amount of gas which falls in 10 to the 5 years, which is here, without the radiation, which is this red curve, is about 100 solar masses. That's exactly what I explained before. You have 10 to the 5 years and an accretion rate in the cold gas of 10 to the minus 3 solar mass per year. So that's because this halo formed molecular hydrogen and cooled down, and the accretion rate slowed down. This one, it's a bit hard to see this curve. That's the one with the high irradiation. So now 10 to the 5 solar masses fall in 10 to the 5 years to the center. So you have a chance to make this supermassive star. Okay, so to summarize this so far is we have these promising sites of 10 to the 8 solar mass halos. If they're illuminated by large radiation, the sound speed is going up by a factor of 10. The mass accretion rate goes up by a factor of almost 1,000 to solar mass a year. We don't see any fragmentation in this kind of simulation. So we end up with a central object which has this mass, 10 to the 5 solar masses, in contrast with the supermassive, the normal massive 100 solar mass star. So that sounds good. The obvious worries next is, well, first of all, I have to explain where do you get this large UV flux. So that's a key part of the story. As I said, if there was no UV radiation, this big galaxy would simply form normal stars. Then the other question is, well, we've done some simulation, but maybe the gas does fragment ultimately into smaller pieces. The entire 10 to the 5 solar masses might not collapse and become part of one star. And then the third worry would be is if this prior star formation, even a little bit in the history of this halo, and you form some carbon and oxygen, they cool efficiently, and again, cool the gas down to low temperatures and prevent this rapid inflow. So if you can still follow the logic here, now I want to explain where you get this large UV flux. So this is actually, as I said, the key. And as I said, this number 10 to the 3, I want the units are 10 to the minus 21 ergs per second per square centimeter per hertz per steradian. What matters here is the following. If you assume that you've produced one ionizing photon per hydrogen atom in the universe, that gives you a radiation density. And we know that's roughly around the time of reionization. When you start to ionize the universe, that should be the background, in the UV background. So this number then would be of order few. So we know that this UV background in the entire universe at the time of reionization, redshift 6 to 10, is about, the background is a few. But here we actually need 1,000 in order to wipe out the molecules and sterilize the gas. And we did come up with a way to get this. So you could actually think of this yourself, but well, there's one way to get such a large radiation for a collapsing 10 to the 8 solar mass halo if it's sitting right next to another 10 to the 8 solar mass halo which has already just formed some stars and is producing UV radiation. This is actually a very, very fine-tuned scenario, but remember, we're looking for rare cases where this happens to explain the very rare 10 to the 9 solar mass black holes. So it's actually okay for anybody to come up with wild schemes, let's say. So this scenario is that here we have two 10 to the 8 solar mass halos. They're forming very close to each other in time and in space. And one of them does precede the other by a very short time, 10 million years or so, starts radiating and illuminating the other one. So then this other one eventually then can avoid. So this one forms stars here, and then later on this one forms a big black hole because it was sterilized by its partner. This actually is fine-tuned, as I said, because you want to make sure that this object here turns on, and then this one should form about 10 million years, within 10 million years later. If you wait too long, then the gas from this halo will be actually boiled away by the radiation from this one. So you can't actually wait longer than 10 mega years or so. Otherwise, you lose the gas from here. You also, that's a very tight synchronization. You also have to be very close. This distance between the two should be a fraction of a kiloparsec. That just comes from, if you actually calculate the units of this radiation, and you ask, can I get that high a flux from the stars which are forming here, and let's say 10% of the gas here is turned into stars, then you have to be half a kiloparsec away to have this large radiation field. That's a very small number. Half a kiloparsec is actually the sizes of these dark matter halos. So in fact, if you thought these were two separate objects, they really should be almost touching, just a few Virial radii apart. Okay, so that's good. You also cannot be too close. There's another requirement. You cannot place this object too close to this one, otherwise it would be tidally stripped. So it's even more fine-tuned. But this is a very numerical question. Do we have such pairs of close and synchronized halos forming in the universe? And the answer is found easily if you run n-body simulations. So this is easier than any kind of hydro simulations I showed, because all we care about is the locations and sequence of time of halo formation. So this is pure n-body. And so we've done this calculation recently, where we took Gadget, public code, run some n-body simulations. They have 600 whatever number of particles. The key is that they're 15 megaparsec on the side, and they have sufficient number of particles to resolve these atomic cooling halos with this whatever algorithm. And so we find that there is actually two such pairs in our simulations. So actually you can see that what happens here, this is as a function of time. This here is the separation on the y-axis of the two halos. And what you see here is this one of the two halos, it reaches here the critical number 1 at this particular time, at 60 million years after, what is it, 60 million years after we started to look at this plot. And then the second one is turned into, and it turns into stars 10 million years later. The gas falls in, and we add 10 million years. That's how long it would take to form stars. So it bursts into stars here, and then its partner is reaching the atomic cooling threshold exactly when it's required, and is actually staying in the right range of 0.2 to 0.5 kiloparsec. For the experts, this is actually two subhalos. So what happens here is we have a bigger halo, and there's the central object in the halo, the dark matter, central dark matter halo, and there's a satellite subhalo, which is crossing the atomic cooling threshold exactly at the right time. This happens twice, and that number is actually perfect, because if you want to match the abundance of these billion solar mass black holes in the observations of 1 per cubic gigaparsec, we would need only to find one such pair if we did 60 n-body simulations. We actually found 2 in 5 n-body simulations, so we're 1 or 2 orders of magnitude even higher than technically required to explain the Sloan quasars. I should also add one more bullet to this model, which is very good, because we're postulating that these two halos synchronize so well. There's no time for metals to be produced in one of the halos and pollute the other. So this also solves the problem of our black hole forming halo not being metal polluted. There's simply no time. There's time for the photons from the partner to sterilize the molecules, but there's no time for any metals to travel and pollute our halo. So that's the good news. So the last 3 minutes, I should say there is a potential ouch, or so I've told you that there's no sign of fragmentation in these bigger halos. If there are no molecules, the gas comes in rapidly. There's no sign of fragmentation. This paper, this is a nice paper which came out a year and a half ago, and they basically simulate the same exact setup, 10 to the 8 or so solar mass, dark matter halo, artificially eliminating all molecules from it. So this only has atomic cooling, and they run to higher resolution than previous simulations. And then what they actually don't conclude anything definitely, but they say that the higher resolution runs do however point to fragmentation at small scales. And in the highest resolution simulation, a sample object of few times 100 solar mass forms with multiple clumps. So what they're saying here is if you run the simulation and really squeeze your computer even more, it's possible that this 10 to the 5 solar mass of gas doesn't go directly to a 10 to the 5 solar mass star. It looks like it might be fragmenting. So we first panicked, but then, well, just a picture of what happens. So this is the simulation, and what happens, they simulate to high resolution, but the disk, a very thick disk, which is gravitationally, which is rotating at like half the Keplerian speed, and is gravitationally marginally unstable, forms in the center. And you can see that it's sort of breaking up, and then these clumps, which you see here, later can, in principle, give you, instead of a single 10 to the 5 solar mass object from this whole thing, could give you smaller mass fragments. So that would be a problem. I think I have 3 more minutes. So we think we can stop panicking, at least because we try to ask ourselves, what is the fate of these clumps? So of course, even this simulation, when clumps form here, they cannot follow the ultimate fate of these clumps because there's resolution limitations. So the way we try to do this is analytically. So we built a model in this paper recently, where we made a toy model of a compact, metal-free, marginally unstable accretion disk. So this model is actually, if you worked on accretion theory, it would be basically a pretty simple toy model for a disk. It's a Shakura-Sanyaev kind of accretion disk, which are normally postulated to operate in quasars. The main assumptions are that this is a steady-state disk, which is processing a constant accretion rate of order 0.1 or even 1 solar mass per year, and that it's in steady state. It's viscously getting heated by gravitational turbulence in the disk, and is balanced by cooling, which is particular to our to this kind of parameter space. It's actually H- cooling. So you can make this toy model for the disk. It predicts a unique profile of viscosity and surface density. So it's a simple model, but it's predictive of when you get fragmentation in the disk. And we were very happy because, so the outcome of such a toy model is that there's a central clump which is already collecting in the center. It has a disk around it, which is a normal accretion disk, and then at some radius you have a clump which forms because inside this radius, this part of the disk becomes gravitationally unstable and fragments. This fragment can accrete and radiate, but the important point is that this model actually works pretty well. It describes the simulations in the sense that the fragmentation radius comes out to be at the few times 10 minus 2 parsecs away from the center, which matches this simulation where it's breaking up. Also, the clumps, you can estimate the size of the clumps in this picture, and they come out with 30 solar masses, which is similar to what's seen in the simulations. In fact, it's even better because we can make a model where we turn down the accretion rate, and this model is also pretty well matches what's found in the earlier mini-halo simulations that I showed you in the beginning. So at least this toy model doesn't seem completely crazy. And the key feature in this model is that the fragments move inward very rapidly because this disk is very turbulent, has high viscosity due to gravitational turbulence by assumption, and the fragments move in on a similar timescale as this viscous timescale produced in the unstable disk. And in fact, what we predict from this model is the fragments sink to the center before they actually evolve into stars. In other words, the fragments cannot stay at the location where they form. The disk torques them and they move them to the center, and that takes less than 10 to the 5 years. So in fact, even if this disk was to break up into fragments, because it's so compact and so dense, we predict that the fragments actually coalesce into a single object. And we also find that even the radiation from the fragments is not enough to destroy the accretion through this disk and the overall behavior. So that's basically the conclusion. We think we can produce rapid infall of gas, 10 to the 5 solar masses, very rapidly in the cores of these halos by eliminating the molecules with high radiation field from a neighbor, and then maybe it fragments, but it doesn't matter. It fragments too late and the fragments move too fast. So that's it. I don't know if I should, it says here 1 minute and 5 seconds on my computer. I could do one slide actually. So this is going to be anyway. So of course the next question you should ask me, how do we distinguish which of these models is correct? Did we form these billion solar mass black holes in one giant burst of forming a 10 to the 5, 6 solar mass black hole seed, which I should have said earlier, if you do this at redshift 10, there's enough time to grow it to 10 to the 9 solar masses. So the second part of 3/4 orders of magnitude is not difficult, even at the Eddington rate. Or maybe we have these stellar mass seeds which merge frequently and one of them grows at the Eddington rate. So how do we do this observationally? How can we tell which was correct? So it's of course hard, but at least let me say that there's some hopes. So one would be, well, directly trying to see these very low mass black holes. So that's the obvious thing you should ask first. Can you actually see 10 to the 6 or less massive black holes around redshift 10 in the universe? And the answer is in principle yes. So JWST, its sensitivity is 10 nanogensky at a few microns, and at redshift 10, if you have a 10 to the 6 solar mass black hole, which is shiny at the Eddington limit, so it's 1,000 times dimmer than these black holes I was talking about, it will actually be visible to JWST, the successor to the Hubble Space Telescope. And I think even in radio, it's in principle possible with the future next generation instruments to detect such 10 to the 6 solar mass black hole. In X-rays, it's difficult with Chandra, but maybe future next generation X-ray telescopes can also see directly. Basically, just below this 10 to the 6 solar mass critical cut, where the two models are very different. Now, another very interesting difference in the two models is the morphology of ionization. Actually, this goes to your question. So, if we have accreting black holes and emitting lots of X-rays, as in the first model, then we assume that then the topology of ionization would be such that the entire universe is partly ionized very early on. On top of this, you might have quasars, larger quasars and stars which shine UV and produce ionized bubbles. But that's actually different from the standard picture where you don't have these early accreting stellar mass black holes, and the ionization happens later and is completely consists of bubbles in a completely neutral universe. So if you're optimistic, again, this is difficult, but with SKA, 21 centimeter cosmology can in principle measure the difference in the power spectra. Now, maybe the best thing to say at this audience, at this meeting, is that of course the great thing would be to measure the find the mergers of black holes through gravitational waves, and ELISA, as proposed, could actually very easily see 10 to the 4 solar mass black holes out to redshift beyond 10 when they merge. The gravitational wave amplitude is detectable, and there should be sufficient events to actually discover them. And the future gravitational wave detectors can go to even lower masses. So even maybe the further down in the merger of these stellar mass black holes, you can actually see them. That would be the obvious way to distinguish the two models. And then the last bit, which I don't think I'll go into again, is you could try to look locally and look at the black hole population in very low mass galaxies. So basically, if all the galaxies had stellar mass seeds early on, then the low mass neighbors of the Milky Way should have black holes in them as well. Whereas if rare galaxies formed 10 to the 6 solar mass black holes, which then grew later, the low mass galaxies should have no black holes. And that should be a distinction. Then the observation here you need is somehow do better kinematics of small galaxies nearby in the cores to see if they have black holes. Currently, we don't actually know whether the dwarfs have a 10 to the 5 solar mass black hole or not. These are our future hopes, and I guess I will end here then. Thank you.
Thanks, Sota, for the very nice talk. So it seems that we have answered almost every question, but maybe there are a few from the audience.
So, do you predict a spectrum of masses for mergers? Do you have a figure to show as a function of redshift and mass?
So
what do we expect?
So I don't think I will dig up the figure, but I do have it in our paper. But I think the basic number was that you do if you go to E-LISA sensitivity, you expect tens of events per year per unit redshift beyond redshift 6. So we're talking about the beyond redshift 6.
Yeah, it would be very good. We can test your model by asking the question, what is the distribution of masses? You know, it will be larger masses closer to lower redshifts, right? So if we have a prediction, then that's something we can, and also Einstein telescope. I'm very much interested in what numbers you predict, what rates you predict at different redshifts. Because Einstein telescope, we can see 100 solar mass black holes all the way to redshift of 20. So that's something we can.
So I mean, the zero author statement here is that there will be many, many mergers of 100 solar mass black holes at redshift 10 to 20 in the first model where stellar seeds. There will be no mergers in the model where just 10 to the 6 solar mass black holes form directly. It will be zero. So there will be a large difference. I do have plots where, and you're right, the mass ratio distribution, the characteristic mass of the mergers, they're different in the two scenarios. Actually, to be fair, we only did redshift 6 and higher. The other papers, I can give you references where they do show this below redshift 6.
Other questions? Students? You can answer more, but ask.
So basically these fluctuations come from Gaussian random fields in the very early universe. And there is statistics of how close two different peaks could be. Is it possible to start from that and then simply looking at how high the peaks are, can you get an estimate of how many such halos should form and whether it's consistent with the observed these high redshift quasars?
So yeah, so when I showed you this merger tree, this basically is what you're saying, because this is you directly can calculate an analytic model actually the rate of mergers at redshift z between a halo of mass m1 and m2. We don't actually have spatial information in these analytic models, but they're calibrated with simulations. And we have merger rates of dark matter halos, which are analytically calculable, and they match n-body simulations. So in fact, when you make these merger tree models, I said it's exactly what you're saying, that we know how many mergers take place at each epoch. So that's true, that's in these models. That's why merger rates are high around few sigma peaks. The very high peaks are too rare, they never merge. the merger rate peaks around 1 or 2 sigma peak.
Anything else? Okay. Now let's thanks Zoltan again.
Thank you.